Hello, everyone. Welcome to our live session for today, Tuesday, August 29th. We're happy to be here. We are in full swing of our semester here at the University of Arizona. We know that you find us from a variety of places. So if you're from our classes, welcome. If you found us through other means, welcome. Make sure you hit the subscribe button and the bell icon so you're notified of upcoming live sessions. My name is Matthew. I am one of the course staff for our online classes. I also help with behind the scenes stuff. Chris, I'm just going to hand this over to you to welcome everyone, and then we'll get started with questions.
Okay, welcome everyone, however you found us. If you're in the online class, that's great, or if you just stumbled into it, it's fine too. I'm ready to take your questions on astronomy.
Excellent. So these happen about, somebody asked if they happen regularly. They happen about every 2 weeks. We generally host these, and we send out a calendar. There's a link to a Google Calendar, and then we also put notifications for the live sessions on our YouTube calendar. So we set these up ahead of time. So if you subscribe to the channel, you'll hear about those upcoming streams. Let's get started with our first question for today, which is from Jeff Martin, who asks, in the far future, will most matter in the universe be inside black holes? Won't most matter currently inside galaxies end up inside their central black hole, or will there still remain free-floating objects?
That's a good question. Black holes, it's one of the myths of black holes, actually, that they will consume everything eventually, or even soon. So in galaxies, black holes represent about 0.1% of the mass of the galaxy concentrated in the nucleus. And while they do grow over time, they simply don't have the gravitational reach to pull in all the stars of the galaxy. So central black holes in galaxies will not devour the galaxy. They will grow, but actually in the end they will starve themselves because there will be no new gas or stars forming nearby. And so even over long spans of time, there's a limit to which the black holes will grow. Another countervailing trend in the far future universe is that galaxies will dissipate. So there will be a gradual process whereby stars evaporate essentially, or move off into intergalactic space and are lost from the galaxy, which of course means they can never be consumed by the black hole. And that process will sort of dissipate a galaxy while the central part concentrates and the black hole grows but reaches some maximum mass.
Excellent, thank you. The next question is from DSC 800. Is the Higgs field the only field that is always a constant in the universe and not subject to being variable or diminishing, such as the inverse square law with magnetism and gravity?
Yeah, the Higgs field, as well as we understand it, is a pervasive field, field defined in the physics terminology, that attributes or ascribes mass to fundamental particles. And it does not seem to vary, or should not in the theory, vary with distance or time. The other thing that has that same attribute, interestingly, is dark energy. Dark energy also doesn't appear to vary with distance from the Earth or with time over cosmic history. And its strength as a force of space-time that's causing the accelerating expansion of space-time also appears to be constant.
Excellent. The next question is from an English major's adventurers who was on with us live. Can you provide a simple explanation of the three-body problem in physics?
Sure. The three-body problem is the fact that physics, the gravity situations, are not deterministic as soon as there are more than two bodies. So Newton's law of gravity, which is a precise equation, dictates the gravitational force between two isolated objects as being the product of their two masses times the gravitational constant divided by the square of the distance between them. And that's an exact equation. However, in all natural situations, there are rarely two completely isolated bodies. There are more than two. Solar system is a good example. Earth, Moon, Sun system is another example. And as soon as you have a third object, the equations are no longer deterministic, which means they have to be solved numerically or with a computer, and they can be done they can be done with a very high degree of precision in a powerful computer, but they're not completely deterministic. And what that means is that the situation is not fully predictable. And so in gravity, we often have the situation of orbits that become chaotic, where very small changes can aggregate over time and lead to wild fluctuations in the gravity force, and even the ejection of objects from a gravitational system. And that's all an extension of this three-body problem, where gravitational physics is not deterministic in the case of more than two bodies.
Excellent, thank you. There's a two-part question next from Pramod. The first part is, can you talk about the significance of India's lunar mission, the Chandrayaan III mission?
Certainly. So the Chandrayaan III mission just recently successfully landed on the moon, and it was a striking achievement for an emerging space power. India's had other successes, and they've been growing their space program for the last decade. But this was a very strong success, because India becomes only the fourth country to soft land on the moon after the US, Russia, and China. And this is the first object, this is the first soft landing in the South Polar region, where we think there's a lot of ice near the surface or just under the surface, and so it's a very good place for a future moon base. So India has homegrown their space industry with a lot of local talent. We already know that India has a lot of great engineers and computer programmers, but they've pulled together a space agency that pretty much on a budget, not with huge funding, not anything like the level of NASA's funding, has been able to do this striking achievement of landing on the moon.
Excellent, thank you. The next question is more specific about the method. Rather than shooting the rocket to the moon, the Indian approach was to boost the orbit incrementally. It sounds like that might be sort of a budget thing, a budget way of boosting the moon. Can you talk about any quantitative advantages that this approach might have?
Yes, I mean, the contrast would be with the Russian probe, which was also heading to the moon around the same time, and which crash landed because there was a failure in one of the rocket systems. And the Russian probe took a shorter, quicker path to the moon, going at higher speed with larger energy costs. So the Indian method is clever because it's an incremental approach. That means the time to your target is substantially longer than the most direct approach, but the energy cost is lower, and I think the risk factor is also lower because you're not having to deal with a very large deceleration when you get to the target for the landing. And so their approach is clearly validated by the success of this mission.
Excellent, thank you. So we have we always get a few kind of career related questions on these sessions, and we don't always pick those because we get them quite frequently. We haven't taken any for a while. So today we'll take these two, and sorry, let me find these real quickly. I was jumping around. Can you talk a little bit about how to get into a career in astronomy? What's kind of a good career path for people who are looking into getting started, and what kind of a path should they pursue?
So astronomy is a physical science, and so the basis of astronomy really is physics and math. And so almost all professional astronomers had a large majority of them anyway, certainly had their first degree, their bachelor degree in physics and mathematics necessarily. It's very unusual to have there are undergraduate astronomy degrees in the United States and a few outside the US, but they're pretty unusual. So in general, physics is the background you need, because astronomy is essentially the projection of astrophysics or physics into space and an application to external celestial objects. So that's what you need a strong background in. The mathematics goes with the physics because astronomers are using mathematical methods that have to be quite sophisticated, and also computation is important, so I'd say some level of computer programming is useful. So that's the background most people have. Now, it is possible to get into astronomy with an undergraduate degree, say in applied math or something like that, more rarely with another science such as chemistry or biology. But it's more of a stretch because in the end you'll be missing quite a lot of the physics you'll need. So it's not like there's only one route into astronomy, but there's one best route that gives you the best preparation for graduate level work, for example.
Excellent, thank you. And then a more so that question was from Karen Lemus. The next question is from Frank Allen, who asks, I'm considering getting a master's degree in astronomy at my age, which is 59. Would it be wise given my age? And what are the latest interesting topics of research that someone might pursue?
I don't know that age is a total determining factor because it really depends on what you want to do with that qualification. If you want to get in like on the ground floor of professional astronomy and build a career in astronomy, then 59 definitely is late to be starting that because you won't be being paid that much. And you may not be able to be in the career long enough before you have to retire to get very far. That alone doesn't have to be a reason not to do it. If you want to get a master's degree to be able to do research, then certainly a graduate qualification is required. Undergraduates taking astronomy do some research in limited ways, but they don't get to do more ambitious research projects unless they have some graduate training. So if you can find a place where you can get a good master's in astronomy, that should enable you to do research, often as part of that program. And if that's what your goal is, then the research is valuable in its own right. It doesn't necessarily matter that it doesn't play into a faculty job or a long-term astronomy job. People with masters in astronomy can get a range of positions in astronomy, not just in academia. They can work at major observatories. They can work at aerospace and commercial sector companies that deal with astronomy. So there are job opportunities for someone with a master's in astronomy.
Thank you. The next question is from a live participant, Société Haitienne d'Astronomie, asks, I wonder why only hydrogen and helium are not metals according to astronomy.
Yes, astronomy has a slightly quirky designation of metals. It's a historical anomaly, if you like. To a chemist, metal means something quite particular. It's talking about the electronic structure or the number of electrons in the outer shell. That's what really determines a metal according to chemistry. Astronomers have developed a sort of simplistic idea of describing metals as anything beyond the primordial elements that are produced by the Big Bang. And that, of course, is hydrogen, the simplest element, a proton and an electron, and the helium that was produced in the Big Bang nucleosynthesis in the first 3 minutes. And they consider that the heavier elements after that are all produced in stars. So it's stars that produce the heavier elements or the metals. But it's a very generic description. Clearly, all the elements heavier than helium are not metals to a chemist.
All right. The next question, we won't take this question. There's a question from Adrian Murray, who asks about Einstein's theory of relativity smacking of Freudianism. I'm not quite sure how Freud is appropriate here. So if you can clarify, Adrian, we can address it. But Chris, can you talk about whether Einstein accounted for some subatomic particles and theories about subatomic particles of gravitation in his theory of relativity?
So Einstein, we have to realize the time he developed his theories. His theories were developed very early in the 20th century. Special theory of relativity was in the first decade, and the general theory of relativity in the second decade. And there were not a lot of fundamental particles known at that time. The electron was discovered or isolated by J.J. Thomson in, I think, 1895. And the proton was, of course, known. The neutron was not discovered until the 1930s by Chadwick, and so that's after relativity. And many other subatomic particles were not well understood at that time. So Einstein's theories are not heavily involved in describing and explaining subatomic particles because there were so few known. They're really dealing with the issues of mass and energy, that's special relativity, and how objects behave moving close to the speed of light. And in the sense of general relativity, they're dealing with explaining gravity as the curvature of space-time caused by mass and energy. Now, in the modern theories, we ascribe a fundamental particle to gravity called the graviton, just to mirror the terminology of other fundamental physics, but the graviton was not understood or conceptualized in Einstein's time.
Excellent. Thank you very much. And he clarified a little bit. Does somehow space-time being curved negate particle attraction? I don't know if you can even address that piece of it.
The issue of curvature of space-time and how particles move is an important part of relativity. Space-time being curved is essentially a geometric description of gravity. And the way particles behave is that particles follow what are called geodesics in general relativity. And these are just essentially the minimum energy paths in space-time, which can be curved paths, of course, if the space-time is curved. So general relativity does ascribe curvature to space-time, and it does describe how particles should move through that space-time along paths called geodesics.
Excellent. Thank you very much. The next question is from Hamid, who's on with us live, who asks, how can adaptive optics be, or why would adaptive optics be a good choice to study faraway objects?
Adaptive optics is a general benefit to imaging of any kind of studying any object, because it is essentially correcting for the fluctuations and turbulence in the Earth's atmosphere that blurs out an image, the seeing, as an amateur astronomer would say. So by sharpening the image, that lets you do two things. It lets you resolve or separate objects that are apparently quite close in the sky, and it also lets you see more distant objects because you're essentially concentrating the light. You're not diffusing it over a larger patch of sky, which lets you see deeper. So in that sense, adaptive optics is always going to let you see sharper and also deeper into the universe.
Excellent. Thank you very much. David Gold asks, how does the anthropic principle contrast with the Copernican principle with regard to Earth?
The anthropic principle is in some tension with the Copernican principle. The Copernican principle, dating from the Copernican revolution, which displaced the Earth from the center of the universe, states that there is nothing particular about the Earth or our situation or our location in the universe. It's the mediocrity principle is another way of describing it. The anthropic principle really puts that on its head by saying that there is something special about us and our situation in the universe, and in fact it's associated with life itself, with the fact that we're biological creatures. And that therefore ascribes something for particular to the nature of the universe such that life could evolve. And we think for life to evolve you need heavy elements, carbon obviously, water. You need planets to form a surface on which life can develop, and the universe has to have some quite general properties for those things to exist. And so the anthropic principle elevates the presence of life and its attributes to a high status in cosmology, where the Copernican principle would go in the other direction and say there's nothing particular about our situation or what we're made of or the fact that we're living on a planet.
The next question is from Wendy Traver, who sent an email. Is there an estimate of the size of the unobservable universe and what percentage of the totality each part observed versus unobserved makes up, and how could that be determined?
That's a good question. So the current cosmology, the Big Bang cosmology, has a calculation of the observable universe, and that's the regions of space, time, we can access in the history of the universe since the Big Bang, 13.8 billion years. And that, because of the superluminal expansion of the universe, faster than light, space-time expanding faster than light for a few billion years, the distance to that edge of the observable universe is about 39 billion light years in every direction. But because the universe has been expanding so fast for much of the early history, we know that that's not the edge of all space-time or all contents of the universe. The trouble is the theory does not, because the expansion was so rapid, especially if you go back to the inflation era, the expansion was so rapid that the theory does not put a fixed number on what the ratio of the unobservable universe to the observable universe is. It could be 100 times larger, 1,000 times larger, 10 times larger. We simply don't know. The theory does not ascribe it. And so we're stuck with the sort of observational limit of the universe, that well-determined volume which we can access with our observations.
The next question is from Peter, who asks, we know that time moves faster in the absence of gravity. In practical terms, do they have to make adjustments to clocks on the International Space Station?
Yes. Well, atomic clocks, there are simple versions of atomic clocks used in the space station, and one had been brought up for an experiment a while back. Atomic clocks are sensitive enough that they can detect the gravitational situation of the space station and how it changes. And these are very small effects. They're about 1 part in 1,000 trillion, 1 part in 10 to the 15. These very small changes in the frequency or the pace of an atomic clock, or how fast time moves based on gravity. And so these are measurable effects. They don't operationally affect anything about the space station and how it operates, however.
The next question is from Ravi, who sent an email. Are charged black holes physically possible in our universe, or are they purely mathematical consequences of general relativity?
It's very difficult to observationally measure and study a charged black hole. So they are theoretical constructs. Most matter, of course, is overall electrically neutral, and so the material that forms a black hole is also electrically neutral. So it's not anticipated in general that a black hole should be charged at all, since it forms from neutral material. But it is possible, of course, that the segregation of matter within a black hole could potentially lead to a net charge. It's just that we have no way of measuring that charge. And so at the moment, the only measurable properties of a black hole are the size, the angular momentum, and the mass.
Excellent, thank you. The next question is from Ned, who is on with us live. Galaxies that form a question mark have been found by the James Webb Telescope. Is that photo enhanced in any way, or does it really look like that?
This photo has got a lot of airplay on the internet in the last few months. It's pretty striking. The question mark that's being discussed and everyone's talking about is part of a very large image that was made of what's called a Herbig-Haro object, which is a young stellar active object. So it's a huge nebula, takes up most of the image, and then off to the side, quite small in the image, is this question mark, and people have shown zoomed in versions of it. And certainly it just looks like a question mark. It's well understood now that it is a pair of interacting galaxies. Interacting galaxies can make all sorts of strange shapes. In fact, there's a sort of amusing thing that you can find on the internet where the people who look at galaxies with Galaxy Zoo, Citizen Science Project, have found interacting or single galaxies that essentially make every letter of the alphabet. So they've made a galaxy alphabet. So given you can make a whole alphabet, it's not surprising you could find a question mark. It's very evocative to have a galaxy interacting, forming something that we would think of as a question mark, but it's just a normal possible outcome of the interaction of two what might be symmetric galaxies, which will be thrown far out of symmetry by the interaction, and that can lead one of them to be pulled into an extended shape, and the other one, the maybe more compact one, left at the dot at the bottom of the question mark.
Next question is from Lysos, who asks, Professor Impey, what odds do you give to life being in our solar system, galaxy, and universe?
Interesting question. So parsing it those three ways, the odds of existing life, that is current life in our solar system, I might put at 50%, because I think it is entirely possible that in subsurface aquifers on Mars there are microbes. I think it's also fairly possible that in the subsurface subice ocean of Europa there's life, and even possibly in Enceladus. Titan, I'm not so sure. So there's definitely, I put 50% in the odds of life in our solar system, existing life, current life. In the galaxy, I'd put it close to 100%, because we know of 20 billion Earth-like habitable worlds in the galaxy by projection. We haven't counted that many. We've surveyed with Kepler the nearby neighborhood and then extrapolated to the whole system. So out of 20 billion Earth-like worlds with all the ingredients for life and plenty of time for things to happen, it seems very unlikely that none of them have formed biology. So I'd put the probability of life in the galaxy at very high, over 99%. And just by extrapolation in the universe with 100 billion galaxies, essentially 100% probability of life somewhere else.
The next question is from Lawrence K., who asks, "Hi, Professor. If the vacuum of space is not really empty and virtual particles pop in and out of existence, where does the energy come to create virtual particles? And have virtual particles ever been observed in a lab?"
Right. So if particle-antiparticle pairs come in and out of existence all the time and are formed from pure energy, where is that energy? Well, the absolute vacuum of space is not a zero-energy state. It's been known since early days of quantum physics, actually, almost 100 years ago, that there is a very small zero-point energy. It's a half the Planck constant, essentially, in the vacuum. So the pure vacuum of space has a small amount of vacuum energy. And you can see the effect of that vacuum energy in the lab. It can actually create a very slight pressure, which can be measurable, and that experiment was done probably 50 years ago. And also in the lab, you can generate or measure the effect of these evanescent particle-antiparticle pairs coming in and out of existence. So this is not speculative physics, this is well-established physics.
The next question is from William Spaziri, who asks, "So many solar systems recently discovered do not have the planet types in the same order as ours. Have we learned anything about how the order is determined?"
We don't know the general architectures of solar systems yet, with the 5,700 exoplanets known. We have many examples of multi-planet systems, some as rich as our solar system with 8 or 9 planets. We also know that the most common type of exoplanet statistically is one that doesn't exist in our solar system, a super-Earth. So planets that are a couple of times the size and maybe 5 to 8 times the mass of the Earth. And the ordering of planets is also sometimes different from the solar system, because we found a number of hot Jupiters where these massive planets, which we only find far from the sun in our system, are found very close to the sun, parked on tidally locked orbits. So all of this means the simple answer to the question is no, we don't have a generic or overall ordering for planets in solar systems in general, because the diversity of the solar systems means we can't determine what the general rule is. We found a variety of different architectures.
The next question, we've got 2 questions that are related to the Chandrayaan III mission. The first one is on with us live. John V would like to know, how will the discoveries made by Chandrayaan III on the south pole of the moon be helpful to all space agencies in order to plan future space missions?
Well, the main thing that Chandrayaan III will do, the lander and then the rover that's going to do the work, is it's going to be very direct evidence of how much ice is right there at the surface of the moon's southern polar region. The thing that will benefit all space agencies and all countries that ever go to that part of the moon is to know where the raw material is that you would need to have water to drink, to grow potentially crops in a base, to separate into oxygen to breathe, and also to make rocket fuel out of. So water is an incredibly valuable resource on the moon. And Chandrayaan is, by direct inspection with the rover, is going to put some numbers on it in one location, but it's a very prime location within a few hundred miles of where the lander is. It's estimated that there are enormous ice deposits.
Sorry, my mouse got stuck. The next question is from Peter, who sent an email. Given the latest moon landing by Chandrayaan III and much discussed plans to establish bases on the moon and Mars, both of which are hostile environments, do you think that living on alien worlds can inform us how best to adapt to climate change on Earth?
That's an interesting question, because some people think we have plenty of problems on the Earth, so why should we be off there on other planets trying to live in these inhospitable environments? And I'm sympathetic to that point of view. We clearly should solve the problems of the Earth and climate change. Could these situations inform our efforts with climate change? Indirectly, yes, because the ability to live on a very hostile world like the Moon or Mars requires you to use technologies that make you completely self-sufficient. In other words, you have to conserve energy, you have to develop the resources to live from a very inhospitable environment of very poor soil, of an ultraviolet and cosmic ray irradiated topsoil that is essentially dead, and you have to live off the land essentially. So these technologies that will be required for anyone to create a moon base or a Mars base are technologies that would also apply to the Earth, let us live more parsimoniously on the Earth with a very small footprint. And that is a valuable thing. Now, whether those technologies are scalable enough to really apply to large fractions of the people living on the Earth is unclear. But we thought that about solar power originally. So solar power was not very economic for several decades and now has become fully competitive with fossil fuels. So once you have pioneering technologies that allow you to live in an energy efficient way, then once you scale them up, you can apply them to large populations.
The next question is from Mr. P. Professor, although SETI-type programs are extremely interesting, what discoveries have we made? And then the second part we'll address after this.
So SETI programs are interesting, and they have essentially not succeeded. So SETI's been going formally since 1959, and Frank Drake's project OSMA, which was listening for radio signals around 1420 megahertz from 2 stars. Very modest beginning to the SETI program. And in the the 70 plus years since Project OSMA, there have been much bigger scale listening experiments with radio telescopes, and some listening for optical pulsed signals from an intelligent civilization, and they have all failed. There have been no indicated signals from an artificial source that survived all the inspection they have to be sure of that. So what have we learned? Well, we've learned not much. We've learned that the nearby universe is probably not littered with intelligent and technological civilizations, or we would have heard from them, we would have seen them, we would know we were not alone. So maybe they're quite sparsely distributed. And the longer the silence of SETI goes, the more likely it is that intelligent civilizations are quite rare, and that we may be the exception rather than the rule.
The next question, you alluded to this, but regarding SETI, will we try to deploy more advanced receivers or transmitters in the near future, such as X-ray communications? And then you also mentioned other technologies. So what do you think is the future of listening and communication in SETI?
Well, SETI is interesting because it uses the technologies that are available to us. And you can critique it on those grounds, of course, because we don't know these are universal technologies. Intelligent creatures may develop other technologies, and we might in the future. Radio transmitters have been around for a century, and we have very powerful radio transmitters, gigawatt, terawatt radio transmitters, so we can beam radio information and listen to beamed radio information very sensitively around the universe with things like the FAST telescope in China, which is 500 meters across. That's being used for SETI too. So that's a very efficient technology. It takes a low amount of power to produce a radio wave. Radio waves travel quite freely through the universe at those frequencies of below a gigahertz. And so that's a reasonable strategy. Optical methods are a little less clear because optical light is extinguished by dust in the interstellar medium, and so the galaxy is fairly opaque to optical light. It's not clear that that's the best message to send or the best messenger. And you might argue that in the far future we'd be using something totally different, maybe neutrinos or gravitational waves, both of which travel very efficiently and freely through the universe with almost no deflection or obscuration. So maybe it's just a matter of the timing of our technology that we're using optical and radio methods. And we might imagine, of course, that another civilization may be using methods we're not familiar with and wouldn't even recognize.
The next questions, there are two questions that are related, even though they might not know they are. Hora asks, what exactly is dark matter and dark energy, and how does it affect the universe?
Dark matter and dark energy are the two most ubiquitous components of the universe. Normal matter, the stuff we're made of and all stars and galaxies, represents 5%, just under 5% of the cosmic pie. Another 22 to 25% is dark matter, and the rest, 2/3 to 3/4, is dark energy. Dark matter is a subatomic particle, we think, as yet unidentified, that is ubiquitous, so as abundant as protons and electrons, that does not interact with electromagnetic radiation. That's why it's dark. But it constitutes most of the gravity in the universe because it dominates normal matter by a factor of 6. Dark energy is something entirely different. It seems to be a property of space-time itself. It's an attribute that has negative pressure and is causing space-time to expand at an accelerating rate, and therefore the universe to expand at an accelerating rate.
And the related question is from Muhammad, who asks, what could be the possible reasons for a galaxy to have orbital speed where the innermost part has a higher speed than goes down, and the brims again have higher speed?
So the rotation of galaxies, so-called rotation curves that were first measured using radio methods in the 1970s and then optical methods soon afterwards, these were the original type of data that were used to infer the presence of dark matter. So if you think of the solar system, then the orbits where most of the mass of the solar system, the 99.9% plus, is in the sun, then the orbits of the planets decline according to Kepler's laws, monotonically as smoothly as you go out. That's not what's seen with galaxies. And so given that the rotation speeds in galaxies rise and then stay flat or continue to rise to the visible edge of the galaxy, that implies that they must be driven in their motions by invisible mass that is mostly outside the visible region of the galaxy. And these are now the dark matter halos that we think all galaxies are embedded in. So that evidence first came out almost 50 years ago, and time has not diminished its reason for us believing that dark matter exists and is the major component of every galaxy.
The next question is from Stan, who sent an email. What is your opinion on the existence of tachyons, and could they be superluminal? Would that also, in essence, permit backward time travel, violating causality?
Tachyons are, by definition, superluminal because they're defined as faster-than-light particles. And so they are superluminal, they move faster than the speed of light, and they are essentially a violation of special relativity. So special relativity declares the speed of light to be a fundamental limit, because as you try and move towards the speed of light and then exceed it, you end up simply putting energy into mass and increasing the inertia of that mass, and so you never get there. So tachyons are a sort of a sleight of hand of theoretical physics to hypothesize particles that exist beyond the realm of special relativity. And that's the reason that astronomers and physicists are really skeptical that they exist. We have no evidence for tachyons, we've never seen them, and they don't sit within the theory of special relativity. And yes, it is possible because of a tachyon to set up an acausal situation where causality is broken. Another reason perhaps to not believe in their reality.
The next question is from Eva, who's on with us live. How do laws work at the International Space Station?
So the International Space Station is a collaboration between roughly 20 countries that have all been involved. They've all had astronauts up there that have all contributed to the maintenance and upkeep and the construction also of the space station. And they are subject to international agreements. So the space station construction and operation has its own set of agreements, which the signatories are the countries that collaborate on the space station. This has become tricky very recently, of course, because of the situation of Russia. Russia was an initial partner of the space station, but essentially doesn't want to be involved in the future. And so these international agreements have to be subject to change because partners can come and go. Certainly partners have been added, and it's possible that partners will be subtracted. China, for example, is not party to the space station because they have their own. So it's a very specific set of laws that govern the space station, set up by the countries that built it and operate it. There is no United Nations treaty that governs the space station, just as there's no United Nations treaty or law that governs how people operate in space. It's up to countries and now individuals and corporations to decide for themselves how they operate there.
Excellent, thank you very much. The next question is from Hank Scorpio, who's on with us live. Gravity is considered to be an attracting force, but has anyone ever considered if something might be pushing matter together rather than matter pulling other matter?
Gravity is an attractive force, and the force that we found that exerts the opposite sense of attraction, which is the pressure force of dark energy. So dark energy is the entity that has this opposite attribute. But dark energy doesn't really operate on mass, it operates on space-time. And so the simple answer is no. Nobody's found something that operates opposite to gravity regarding mass and pushes it together rather than pulling it together, pushes it apart rather than pulling it together.
The next question is from Adrian, who asks, if the James Webb telescope can see back to the origin of the universe, could a more powerful telescope see outside of the universe?
I think not, because the bounds on what you can see with any telescope relate to the way space-time behaves and the way light travels through the expanding universe. So the limit to our vision is called the horizon, the cosmic horizon, and that essentially defines the distance in space-time where light could have reached us in the age of the universe. And that statement and definition doesn't depend on what's doing the observing. In other words, it doesn't matter how sensitive or big or your telescope is or what wavelength it operates at. It's subject to that same limit of the horizon. So the basic answer is no. There's no even more powerful telescope than James Webb that could see any further than James Webb can see. Now, it might get closer towards the Big Bang. James Webb working in the infrared lets it look at very high redshift light, and so it's moving to about 100 to 200 million years after the Big Bang. It's possible you could get closer to the Big Bang than that, but you will not, in a formal sense, see further into the universe.
The next question is from Miles Zitmore, who asks, we hear about the Big Bang, but is there any evidence of multiple Big Bangs? Is it possible that this whole process of creation and destruction in the universe is going on in multiple universes?
It's certainly possible, and the multiverse concept, I'll call it concept rather than a theory because it's not well developed enough to call a theory, certainly posits that out of the quantum creation of our universe, because we do think that it was a quantum event in its inception, perhaps there were other quantum events, other universes with different properties, and essentially other Big Bangs. So yes, as a hypothetical, it's possible. Eventually, if we figure out a quantum theory of gravity or we understand the origin event of the Big Bang better than we do now, we may be able to put flesh on the bones of the multiverse idea. But at the moment, it's just a concept.
The next question is from one of our live participants. Let's see here. So Société Hertzienne d'Astronomie asks, why do we still count gravity as one of the four fundamental forces, since general relativity proved it's instead a curvature of spacetime?
Well, it is one of the fundamental forces because it has a distinct attribute of relating to spacetime and its curvature. The other fundamental forces operate in different ways. Electromagnetic force is also an infinite range force relating to photons, and then the other two forces are confined within the atomic scales. So it has its own particular attribute that places it as one of four fundamental forces. Relating those four forces in an overarching theory is something that people have been trying to do really for half a century, or even since Einstein tried in the 1940s and 50s. and no one has succeeded in unifying these four forces. So at the moment physicists still choose to talk about the four fundamental forces of which gravity is one.
The next question is from Crom Croy, who asks, how big is the accretion disk for a young black hole as compared with, larger, supermassive, and older black holes?
So a small black hole, a dead star black hole, has an accretion disk, the Schwarzschild radius of a solar mass black hole, which is the event horizon size, is a few kilometers. And the accretion disk typically operates on scales that are hundreds to thousands of times the Schwarzschild radius. So for a solar mass type, or a few times the mass of the sun black hole, a minimal black hole, you're talking about an accretion disk that's on scales of thousands or tens of thousands of kilometers, so quite small. As the black hole grows, the mass grows, pulls in matter from larger regions, and the accretion disk grows too. So accretion disk sizes scale with black hole sizes pretty well. And so once you get to the centers of galaxies, those accretion disks have gone millions of times bigger than the thousands of kilometers, and they become the size of solar systems.
So the kind of follow-up to that question is, is the event horizon of a young black hole a fraction of the size of the object, or would it be the majority of the size of the object?
Well, the event horizon by definition is the size of the object. That's how we define the size of a black hole. It represents it's not a physical barrier, it's an information membrane. It defines the region from which nothing can escape, not even light. And so operationally, event horizon size is the Schwarzschild radius. They are the same thing.
Excellent, thank you. Arif Roni is on with us live and has a question, and I'm just going to put it into two parts. Sir, is a Dyson sphere inevitable for an advanced civilization?
I don't think a Dyson sphere is inevitable. A Dyson sphere was a concept from Freeman Dyson, very famous physicist, talking about how an advanced civilization might harness more than a tiny fraction of the energy of its star. So the Earth intercepts about a billionth of the sun's light, and we usefully use a small fraction of that. So the Earth, operationally, our civilization probably uses about a trillionth of the sun's total energy. It's a tiny fraction. The Dyson sphere is a concept whereby a civilization will build an energy trapping sphere closely around a star. Now, it's not a solid object because that would not be stable, so it's more of a lattice work of collectors and concentrators, and so collect a substantial fraction of the energy of the star and then beam it to the planet so that it could use that energy. And that, of course, boosts the amount of energy the civilization is using by factors of millions or billions, I mean, huge amount. So Dyson sphere is a fantastic technology far beyond our scope, and so it's not at all a given that any civilization could have made a Dyson sphere. It would have to be a very advanced civilization that could do that.
So then the follow-up question to that is, do you think that humans will observe another civilization's Dyson sphere, or do you think that they would contact us before we would see? Do you think they would be so advanced that they would contact us before we would observe an object like that?
So astronomers are trying to detect Dyson spheres. There's at least one paper I know of in the last decade, and there may be others, which has done searches for Dyson spheres. So the way you find a Dyson sphere is you find a star and you actually look for no energy trapping sphere is completely efficient, so it will radiate waste heat. And so you're essentially looking for the waste heat of the Dyson sphere. So it's an infrared imaging method. And so those methods have been used, and no clearer signature of a Dyson sphere has been found. The signature is a little ambiguous anyway, so it's not an easy experiment. So yes, we've done some searches and not seen any Dyson spheres. It's not necessarily a given that a civilization that could construct a Dyson sphere would have automatically contacted us. That is ascribing a cultural motive or a psychological motive to a civilization rather than talking about their technology. There are reasons why civilizations may not want to communicate, may not be interested in communicating, even though they have the technology to build a Dyson sphere.
The next question is from an email. Since exomoons seem to be more fertile ground for harboring life than exoplanets, I'm wondering if an exomoon can be the same size as its host planet, or is size part of the definition of a moon?
Generally, moons are smaller than the planets they orbit because they form from material left over from the planet formation. Think of the moons of Jupiter or Saturn. And also, in the terms of those moons, even the largest moons of Saturn, which would be Titan, or the largest moon of Jupiter, which would be Ganymede, they are very small fractions, tiny fractions of a percent of the mass of the planets. So you're not able in planetary science or in the accretion of matter to form solid objects. You're not able to form very large moons relative to a planet. So the biggest exomoons are still, they may rival the size of our moon, and maybe hypothetically an exomoon could be as large as the Earth, but it would be orbiting an enormous planet. As for the ability to life to exist on an exomoon, it's certainly possible. We have moons in our solar system which could be host to life, and if there are even larger exomoons or in other solar systems, then they become even better hopes for life. At the moment, however, exomoons are extraordinarily difficult to detect. There are few contested claims in the literature, and I suspect the first exomoons will be discovered quite soon, but at the moment we aren't really able to study exomoons.
The next question is from an email. Can you talk about what is the escape speed of the solar system, and how is something like this calculated? It comes up because Avi Loeb said that Oumuamua seems to exceed this speed.
Right. You calculate the escape speed of the solar system by just imagining what velocity an object would have if it was launched from the surface of the sun to eventually reach infinite distance. And obviously that speed is something larger than the speed of the outermost planet, Uranus and Neptune. It's a factor of 2 larger than that. So any object with more than twice their orbital velocity, in principle, is not bound to the solar system. And therefore any object we see moving through the solar system with more than twice the orbital speed of Uranus or Neptune is not a bound object and is an interstellar object. And that's what we think Oumuamua was. It's an interstellar object on a transient trajectory through the solar system. First one ever discovered, but it could have happened before with other objects that we didn't observe.
Excellent. Thank you very much. I know we have to end a little early today due to some other team commitments, so we'll take one final question for the session today. One of our live participants would like to know, isn't it counter-logical to consider the Big Bang Theory without a place to consider the center of the universe?
Not necessarily. The Big Bang Theory posits that space-time was all originally confined to a long time ago, 13.8 billion years ago, an iota of space-time that expanded in every direction. So it was a uniform expansion. And at every stage in this expansion, there's no center to the expansion because the space-time is unfolding uniformly across all space and time. And so now in our old empty universe, we see galaxies all moving away from us, but we could move to any location in our large expanding universe and see the same thing. So there's a democracy or a sort of Copernican principle in operation. So the positing of a Big Bang itself does not imply a privileged position for any subsequent part of that expanding universe. It's a good question to end with, and a lot of interesting questions this week, and thanks for those, and thanks to Matthew for facilitating. And we have a couple more on the books a couple of weeks from now, so we'll see you soon.
Excellent. Thank you very much, everyone, for joining us. We really appreciate it. The next live session will be September 9th. And again, to address one of the questions from earlier, there's not really a set schedule. We do it twice a month, and we pick those according to our schedule, and we try to do them about 2 weeks apart. There's the next one is going to be September 9th, or sorry, I apologize. I said September 9th, but it's September 13th. September 13th is the next live session, and September 29th is the one after that. So we will see you all in a couple of weeks, and we hope you have a good rest of your week and weekend. Take care, everyone.